Hey everybody, Doc here again. We're at week 3, day 11, chapter 3, section 9. Now we are going to get into antiderivatives. So what is an antiderivative? Well, it's doing the opposite of differentiating. So once you have a derivative, we know that that function is a slope function or a rate of change. If you go backwards, then you're going to get your position function or your original function. And a lot of times that's needed. So let's say sometime we have our velocity function and we need to find our position function. Then we would go backwards and we would use an antiderivative. So first we're going to take a look at how we do basic antiderivatives. Now, there's a couple notations for this, okay? You could start with little f of x and then go to capital F of x. So this would be the first derivative and this would be the original. Or you might do this. Okay, so you'll see both of these in your book. All right, so let's consider a slope function. Let's start out easy and let's consider a slope function of f of x is x squared. Now, you can use what I call the opposite power rule. They still call it the power rule. It feels kind of weird to me since we already have one called the power rule for derivatives. But anyway, we can find our original or the function I'm going to take the x value, add 1 to the exponent, which shouldn't surprise you because before we subtracted. So now we're going to add 1 to the exponent, and then we're dividing also by that value. Okay, so the thing is with this, let's take a look. It could be x to the third over 3 for the one that we just did. Okay, so f to the third over 3. So we're going to say this is f prime of x, and we get x to the third over 3. Now, answer? Maybe, but the fact of the matter is that I could also have this like plus 5 on the end, and when I differentiated it, I would still get x squared. Or I might have x cubed over 3 minus 1/2. If I differentiated that, I would get x squared. So how do I know what constant value I'm adding on? Well, we simply put a c on the end here for constant. And that indicates that we know that there could be a constant there. Sometimes we will solve for what that constant may be given some other information. And sometimes we will just leave it plus c. Okay, so we have f of x equals x to the n plus 1 over n minus 1 plus c. And that is if little f of x equals x to the n. So here is the notation where we're using this for the rate function and this for the original function. Okay, so here we go. All right, so let's take a look at the result for that. We said will be f of x is x to the third over 3 plus c. Now this would be our final answer to finding f of x once given the rate of x squared, x cubed over 3 plus c. And the c means it could be any constant, or we don't know what the constant is because we don't have enough information at that time. Okay, so we're going to find the derivative of a couple things, and let's look at example 1. Example 1 says, what about sine of x? Okay, what about sine of x? So now we need to use our brains a little bit. We say, okay, if I differentiate something and get sine of x, how do I differentiate something and get sine of x? Well, we're going to have to use our thought bubble here. I'm thinking, well, if I differentiate cosine of x, I get negative sine of x, so that's close. So what could I do so that I can make sure that if I differentiate something, I get sine x? Well, if I start out with a negative in the front, negative cosine x, and I'm also going to have plus c because I don't know, there could be a constant there. Then if I went through and did the first derivative of that, I would have a negative of a negative sine x, which would give me my sine x. So knowing your derivative functions or your trig functions very well, very important, because you're going to have to toggle back and forth between the two of them to make sure that you can find your antiderivatives. All right, now B in that example 1 is just finding the power rule that I already gave to you. So I'm going to skip that and we're going to go take a look at example C. Example C says f of x equals x to the negative 3. So we know here by inspection already that x cannot equal 0 because this is 1 over x cubed. So that we want to make sure that we recognize. And we want to, again, use our power rule to solve. So I'm going to have, I started with little f of x. I'm going to have large f of x equals x to the, if I add 1 to this exponent, I get negative 2. Same goes on the bottom over negative 2. And I was going to simplify that a little bit. I guess we could just write negative 1/2 x to the negative 2 plus c. Now you might be thinking, well, why don't you put that x on the bottom of the fraction? You could. The reason I didn't was because this is the form that it started with, so I left it in that form for that problem. Okay? But it wouldn't be wrong if you did. Alrighty, so let's take a look at example 2. Example 2, g prime of x. Here we're starting with g prime of x equals 4 sine x plus 2x to the 5th minus the square root of x all over x. Now, at first I look at this and go, oh my goodness, so we're jumping right into it. Might as well, just jump right off that cliff. But it's actually not that bad. So first we're going to split this up. And we see we have 4 sine of x plus, if I simplify this, I just get 2x to the 4th. And if I simplify this right here, I will get minus x to the negative 1/2. Okay, so that is just simplifying. I didn't take the antiderivative of it yet. I just changed it to a nicer form so that now I can. So here we go. We have g of x, our original function. Now we already know that when we are taking the antiderivative of sine, we get negative cosine. So this is going to be negative 4 cosine of x plus 2x to the 5th over 5 minus x to the 1/2 over 1/2. So now I have negative 4 cosine of x plus 2/5 x to the 5th minus, invert multiply here, I'm going to bring this up, 2x to the 1/2. Now, don't forget in the end, I need to make sure that I put my plus c. Okay? And this is my final answer for my antiderivative. It's not too bad. Let's look at example 3. F prime of x equals x to the square root of x. Now, first thing I want to do is change that to x to the 3/2. Okay? So, it says find f if f1 equals 2. Okay. So I am first going to take the antiderivative, and I have x to the 3/2 plus 1 would be 3/2 plus 2 over 2. So that's 5/2 over 5/2. And then I just put plus c. So if I clean that up a bit, that will be 2/5 x to the 5/2 plus c. Now here they want us to find out what my c value is, and I can use the information they gave us above, that f of 1 equals 2, and I'm going to substitute. Actually, I'm going to rewrite this down here so you can see my substitution directly below it. All right, my f of x is equal to 2 equals 2/5, and my x value is 1 to the 5/2 plus c. So here I have 2 equals, this is just 1, 2/5 plus c, and when I subtract 2/5 from both sides, I'm going to take 10/5 minus 2/5, because a 2 is 10/5. So 10/5 minus 2/5 will give me 8/5 for my value of c. So my final answer for that information given to me would be 2/5 x to the 5/2 plus 8/5. Okay. All right, let's take another look at another problem. We're going to do example 4 next. Example 4. Find f if, f double prime of x equals 12 x squared plus 6x minus 4 if I have f of 0 equaling 4, and make sure one of these isn't a prime. I'll go back and look at the book here. Yeah, f of 0 is equal to 4, and f of 1 is equal to 1. Okay, so first I'm going to solve for the first derivative. So I take this and I take the opposite power rule to find f prime of x. That will give me 12 x to the 3rd over 3 plus 6 x squared over 2 minus 4x plus c. Okay, simplify that. That will be 4x cubed plus 3x squared minus 4x plus c. Okay, now f of 0 equals 4 will help me with this solve, and I will get a result for c but I can't use that yet because I only have f prime of x. So I have to take it one more time. Let's do it again. 4x to the fourth over 4 plus 3x cubed over 3 minus 4x squared over 2 plus, notice what happens here, cx plus, we can put another constant, so we'll use d, just go in alphabetical order. So that makes things a little more interesting. So now I have x to the fourth plus x cubed minus 2x squared plus cx plus d. And f of x is equal to this. All right. Now I can use the information that I have to solve for C and D. And I really want to take particular attention to the f of 0 because I know that I can put 0 in for x, and that will help me get rid of the C value here to first solve for D. So let's do that. So we're going to say 4 equals 0 plus 0 minus 0 plus 0 plus D. So we see that D equals 4. So now that I know that D equals 4, I can substitute it in. And now I can use the second point that I have to help me solve for C. So let's try that. I have f of 1 equals 1, so that'll be 1 equals 1 to the fourth, 1/3, 2 times 1 squared, plus c times 1 plus 4. Now let's take a look at what happens there. 1 plus 1 minus 2 plus c plus 4. So this is 2 minus 2, and that's gone. And then I'm going to take my 4 over, and I get c will equal -3. Okay, c equals -3. So again, I just plug my 1 value in and then solve for c. So my final equation. X to the fourth plus x cubed minus 2x squared. My c value is -3, so -3x plus 4. Okay? That is example 4. Now example 5 we're going to discuss. Let's take a look at it. Let's say that you were given the slope function as a graph, and you had to use that slope function as a graph to find the original function. Now this is a little trickier, but you need to remember that these values that are on this line here at these x values are slope values. So for instance, the slope at, we'll say, 0.2 is down here somewhere, whatever this value is. And it is a negative value because it is below the x-axis. So that means the slope at that point of that graph would be negative. Now, the slope continues to be negative until I get to 1. And then my slope is 0. So my slope is 0. That tells me that there's going to be some kind of critical point at 1. Then my slope becomes positive, okay, all the way up here. And then we need to take a look from where it changes from increasing to decreasing. And we may have horizontal tangents, which would then give us possibility of having an inflection point. So if you see 1 and 3 here at your zeros, 1 and 3 will give you horizontal tangents. So you know that positive, f of x is positive, it's increasing, and you see it has a local minimum at x equals 1. Then a local maximum at x equals 3. Okay? So let's take a look at this graph. Now, how do we know that it started at 0, 2? Well, they gave us the point 0, 2. So that was good. So they gave us this point. You can see that I have my critical points right here. And then I have my inflection points where I go from concave up to concave down, and then another inflection point, the concave up again. Okay? So those are a little tricky, but if you take a look at both of them side by side, bit by bit, you can make sense of them. All right, let's look at example 6. Example 6. Okay, example 6 is a particle moves in a straight line, has an acceleration given by this a of, with respect to time, 6t plus 4. And it has an initial velocity of negative 6 centimeters per second. An initial displacement at 9 centimeters. Find the position function. Okay, so let's take this step by step. We know that we have an acceleration function, and an acceleration function actually comes from a velocity function. So if I take the antiderivative, I'm going to be actually solving for the velocity function. And I will get 3t squared plus 4t for my velocity function. Now, I can't forget my c value. Now I want to look at the information because I would really like to know what c is, and I can see that if I plug in my initial velocity right here, which gives my x value of 0 and this being negative 6, then I can do that and have negative 6 equals, if I plug 0 in for t, that's just 0 plus c, and that would be c equaling negative 6. So now I can finish my velocity function. And I need to do it one more time in order to get my position function. So I can solve for my s of t, 3t cubed over 3 plus 4t squared over 2 minus 6t, and again I have a c value. Well, lucky for me, they also gave me the initial displacement, so I can solve for that c value by putting 9 equals 0. Well, I didn't simplify this, so let's do that real quick. T cubed plus 2t squared minus 6t plus c. So this would be 0 plus 0 minus 0 plus C. So I see that C equals 9. T cubed plus 2t squared minus 6t plus 9. That will be my position function. And that is what they asked me for. So there's our answer. Okay. Example 7. Let's see, I better start a whole new page for this one. Now, example 7, we're going to use the information that if we have a motion that's close to the ground, we can use the gravity constant. And the gravity constant, which is represented by G, is going to be about 9.8 meters per second, or 32 feet per second squared. This is squared too. Okay, so that's motion close to the ground. We can assume that that G is constant. Now, example 7 says a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. We're going to find its height above the ground t seconds later. When does it reach its maximum height, and when does it hit the ground? Okay. And that is on 272 if you're looking in your book. So the first thing, we want to write down the things that we know. So we know it's 48 feet per second. We know it's 432 feet above the ground. We want to find maximum height. And we want to know when it hits the ground. Okay, so first, acceleration. Well, we know that acceleration, just by our physics knowledge, dv dt is negative 32. And we can differentiate that to find the velocity function. Negative 32 t plus c. Now I know my initial velocity is 48 feet per second, so I'm going to actually use that information to solve for c, and that'll give me 48 equals negative 32, and we put 0 here, plus c, so c is 48. Plugging that in to my velocity function. And now I want to go one more step and find the position function. And then after I do all that, I can answer my questions. And I see that I have, again, another constant. So I'm going to we'll call it D this time, since I already used C before and it was defined as 48. And we'll call it D. And we see that it is 432 feet above the ground. So that would be my initial start place. So that would be 432 feet equals, initially at time being 0. So D is going to equal 432. So my position function will be negative 16 t squared plus 48t plus 432. Now, the question is, when does it hit the ground? Okay, when does it hit the ground? So I'm going to take a look at that, and I guess I should do the maximum height too. I'm going to need the first derivative, but since I'm right down here, let's go ahead and look at when it hits the ground. Negative 16t squared plus 48t plus 432. I'm going to set it equal to 0. So I want to know when my position goes from 432 feet high to 0. So I need to simplify this, and thank goodness I can simplify this by 16 here. And I have t squared minus 3t minus 27 equals 0. And when I solve for that, I'm going to have to use my wonderful quadratic formula. So x equals negative b plus or minus the square root b squared minus 4ac. All of that is over 2a. I'm going to simplify that and get 3 plus or minus the square root of 117 over 2. Now, I can see that 9 does go into that, so I'm going to factor out the square root of 9. So I have 3 plus or minus 3 square roots of 13 over 2. Now, I'm going to think about this. Am I going to get a negative value? Am I going to get a positive value? Well, I'm talking about how many minutes before it hits the ground. So I'm not going to use a negative value. So I have 3 plus 3 square roots of 13 over 2 will be my value for the time when it hits the ground. All right. Now, we also want to find out when... I'm pretty sure they wanted us to find out the maximum height. Yep, maximum height. So we're going to set the velocity function equal to 0 right here. And I have 0 equals negative 32t plus 48. I'm going to subtract 48. Divide by negative 32, and t will equal 3 halves. And 16 will go into both. So that's after 1.5 seconds, because it's measured in seconds, is when its maximum height would be. Okay, now it doesn't ask us for the maximum height, so we don't have to put that number into anything to find out where the height would be, but we could put it into the position function and see. So at about 1.5 seconds, it'll be at the maximum height, and in case you're curious, it'll hit the ground after, this will be approximately 6.9 seconds. Okay, so this is about 6.9 seconds. And this was 1.5 seconds for maximum height. Okay. All right, I guess that's it. That's example 7. That is all for that section. Kind of surprised. I thought there was more. Okay, so done with 3.9. And that'll be it for today, and I will talk with you soon.